In the midst of the desolate Taklamakan Desert, a railway stretches for more than 2,000 kilometers, slicing through an endless ocean of golden sand. This immense engineering endeavor drew the attention of experts around the globe, even in the United States, who marveled at China's relentless determination. It was a monumental project that cost over $3.5 billion and engaged more than 12,000 workers over 10 years, now standing as one of the most impressive modern marvels on Earth. But how did engineers manage to push through brutal sandstorms and unrelenting heat to forge the longest desert railway network on the planet? Today, we journey into the story behind one of China's most extraordinary feats of modern engineering. For decades, China's vast northwestern region, Xinjiang and the Tarim Basin, remained an empty space on the map, a region divided by towering mountain ranges and buried under the immensity of the Taklamakan Desert, which spans more than 127,000 square miles. In summer, the surface temperature scorches beyond 160 degrees Fahrenheit, and in winter, the cold plummets to -13. It is a land without water, without power, where beneath the feet lies nothing but shifting dunes, with no solid ground to build upon. Yet, beneath this barren sea of sand rests an immense treasure, billions of tons of untapped natural wealth, oil, coal, and above all, rare earth minerals, the very elements that fuel global technological power. To access these resources, China faced a challenge once dismissed as impossible: building a railway straight across the desert. Thus, the Hotan-Ruoqiang Railway was born, an 890-kilometer stretch forming part of the Taklamakan Desert Loop, a 2,685-kilometer circular railway line running along the desert's southern rim. Completed in June 2022, it became the world's longest railway traversing a desert. Before the first rail was ever laid, Chinese engineers confronted a fundamental question: how do you chart a path across terrain that never stands still? Using high-resolution satellite images, ground-penetrating radar, and thousands of wind readings, they mapped the dominant wind directions, shifting dunes, and zones of relative stability. Survey teams ventured deep into the desert for months, drilling hundreds of test holes, some plunging tens of meters, to study the layers hidden beneath the sand. Every marker they placed was measured by hand with precision down to the centimeter. The route had to steer clear of wind corridors where sandstorms could sweep away entire trains, while remaining close enough to oil and coal fields along the Tarim Basin. This was the first stage in transforming what was once a blank void on the Chinese map into a continuous steel arc winding around the desert's edge. But before true construction could begin, an equally vital mission awaited: taming the moving sands. Hundreds of local farmers were called to perform a deceptively simple yet decisive task: anchoring the desert floor. They bundled straw, twigs, and bamboo into long sheaves and planted them in a checkerboard pattern, each square measuring exactly 1 meter and tilted diagonally at 45 degrees instead of forming straight lines. This clever design disrupted the wind's direct flow, scattering its strength and forcing the sand to settle within each grid. Under a merciless sun, in temperatures over 140 degrees Fahrenheit, workers pressed each bundle deep into the dunes, covering them with extra twigs for reinforcement. Slowly, these grids spread outward, thousands of woven straw fences stretching to the horizon. Within months, the once restless dunes had transformed into a quilt of golden brown and green. The sand no longer drifted, the surface stiffened, and trucks could finally drive without sinking. With the ground stabilized, the true phase of desert construction began. Bulldozers arrived in force, reshaping the terrain, slicing down the towering dunes and redistributing the sand to fill the valleys. Their goal: to create a level, balanced surface strong enough to hold heavy machinery without collapse. Every section was methodically graded and checked by surveyors to ensure uniform height and slope across miles of open desert. Conveyor systems moved the excess sand aside, while compactors pressed the top layer into a firm, stable base. Yet even a flattened desert surface was still fragile. Engineers discovered that by injecting controlled amounts of water into the sand, they could bind the grains together. Long sprinkler systems and underground pipes sprayed groundwater over the site, allowing moisture to seep several inches deep. Once dampened to the right level, massive steel rollers moved in, compressing the surface and eliminating air pockets. The low thunder of metal drums echoed across the dunes as the machines transformed loose sand into a dense, stable platform. When the surface dried again under the blazing sun, it had hardened enough to bear the weight of cranes, mixers, and transport trucks, a foundation literally built from sand and water. Next came the base layer. Trucks poured loads of reddish soil over the compacted surface, which bulldozers spread evenly. This layer added pressure and strength, keeping the foundation from shifting under the intense heat or constant vibration of passing trains. Each section was compacted again, forming a dense and resilient substructure. Once the ground was secure, workers began the monumental task of building the bridges that would support the railway. They had to drill through dozens of feet of loose sand to reach solid gravel or dense soil below. Reinforced concrete piles were driven into the earth using steel casings and bentonite slurry to prevent collapse. Concrete was poured from the bottom upward through tremie pipes to eliminate air gaps, while steel cages were lowered with millimeter-level precision. Even the slightest misalignment could compromise stability. And with daytime and nighttime temperatures differing by more than 130 degrees Fahrenheit, precision was vital. Crews often worked under the calm of night when the winds subsided and the sandstorms eased. These reinforced piles acted like roots, anchoring the railway deep beneath the dunes. Soon, over 11,000 bridge piers began to rise, forming an immense forest of concrete columns that stretched toward the horizon. Each stood between 16 and 50 feet tall, cast with slip-form molds and strengthened with galvanized steel and salt-resistant additives to endure the desert's harsh climate. The short, uniform distances between piers were calculated to absorb the stresses caused by wind and extreme temperature shifts. As the sun dipped behind the Kunlun Mountains, the endless rows of pillars shimmered against the dunes, a skeletal framework of steel and concrete defying the desert's fury. Atop those pillars, thousands of pre-stressed concrete box girders were lifted into position by massive crawler cranes and self-launching gantries. Each girder, over 100 feet long and weighing hundreds of tons, was transported on specialized flatbed trains and carefully set in place. Using laser-guided systems, engineers aligned each segment with precision measured in millimeters. Once secured, bridge decks were poured or assembled from precast panels, forming the smooth bed where the tracks would later run. The spacing between each span allowed desert winds to sweep freely beneath, preventing sand from ever burying the railway. In total, more than 65% of the Hotan-Ruokiang Railway, roughly 310 miles, runs on elevated viaducts. From above, the railway appears as a silver thread, cutting through a golden sea, a living monument to human innovation in one of Earth's most unforgiving environments. Next came the installation of the sleepers, also known as railroad ties, the concrete blocks that keep the rails in place. These were laid evenly along the track bed to distribute the immense weight of passing trains. Workers aligned each sleeper by hand, lowering the steel rails onto them with precision lifting frames. Once fastened, they ensured that the tracks stayed perfectly straight and secure, ready to bear the massive loads that would soon thunder across the desert. Each rail, stretching more than 260 feet long, was hoisted into position by cranes and adjusted with meticulous care. Engineers checked every joint and expansion gap, tightening each clip to lock the rails firmly into the concrete foundation. It took nearly a year of continuous work to lay hundreds of miles of steel across the dunes. Once the final bridge span was completed, the line entered its testing phase. Test trains ran back and forth along the route, measuring vibration temperature, and wind sway. The bridges were stress-tested with trains weighing thousands of tons, and results showed elevation deviations of only a few millimeters, even after hundreds of runs. Thanks to the elevated viaduct design and constant airflow beneath the tracks, sand no longer accumulated along the line. All data streamed into a central control center through IoT sensors and solar-powered monitoring cameras, allowing real-time analysis of every section of track. After 6 months of intense testing, the Hotan-Ruokiang Railway officially opened in June 2022, completing the 1,685-mile loop around the Taklamakan Desert, a continuous circuit of steel and determination. Today, the Taklamakan Desert stands not merely as an obstacle overcome, but as a symbol of coexistence between humankind and nature, a living proof that intelligence, patience, and vision can turn even the harshest wasteland into a beacon of innovation.